Alright, we are going to continue with the certain aspects of contact forces. So as we saw, there is something called as tension. Now this tension basically is a factor which develops in strings. In all your problems you will be basically dealing mostly with massless strings, and you will be dealing with frictionless strings. It doesn't mean that the story ends here. We have strings which are with some kind of friction, or we have strings which have some kind of mass as well. So basically all the problems that we will be dealing here will be massless strings and frictionless strings. Now we are just going to study how we are going to calculate this tension. So for example, if this is a bob suspended by a string, now look at this surface and look at this surface. So this string is in contact with the ceiling or a fixed surface, whatever it is, and this string in this part is in contact with this bob which is of mass m. Now there is a force which is exerted by the string on this surface, and there is a force which is exerted by the string on this, otherwise this would have fallen down. So since this is in equilibrium, we will see that this tension is acting upwards for the bob. However, this tension is acting downwards for the ceiling. So whenever we are going to consider a surface, the tension is always taken, it is always taken as moving in a direction opposite to the surface. So the tension is always taken as moving in direction opposite to the surface. So when we are considering this bob of mass m, how do we balance this? So let's say this is being pulled by a tension T, and this will have a mass of m acting downwards, or rather mg acting downwards. So since this is in a vertical equilibrium, we will say T is equal to mg. So this T is in upward direction. However, in the same string there is a downward direction which will be T, and which will be acting downwards for the ceiling or the fixed surface to whichever it is fixed to. So we have in a how do we represent tension? It depends upon the body which we are covering. Now for this case we are covering the body M, so the tension is going to act outwards from the body M. In this case we are going to cover the tension T in this, so this is outwards the surface to which it is fixed. So this is how the tension is represented. Students might sometimes get confused that if this is the direction of the force of tension and this is the direction, then these will cancel each other, they are acting on the same body. No, we are actually referring to tension acting on the bodies which are connected to this string. So on this there will be a tension which will be acting downwards. This is the surface which is fixed. So let's say this is a fixed surface or ceiling, whatever it is. On this body there is a tension which is acting downwards. However, on this one there is a tension which is acting upwards. So on this one the tension will be acting upwards. So I hope we are clear on this. Now tension is always going to act moving away from the body, moving away from the body, moving away from the body. And the second rule for applying tension is tension in the same string is always going to be the same, is always going to be the same. So tension in the same string will always remain the same. For example, if we have obviously there is only one string out here. If we have a case like this wherein we have suspended a mass like this and there is a fixed surface like this, so we have a mass which is suspended like this and this is in equilibrium. So we have a fixed surface to which this is attached. For this surface the tension will act in this direction. For this mass the tension is going to act in this direction. Now let's come to this point. For this the tension will act in this way, and for this the tension will act in this way. However, this T is not going to remain the same. It's going to change now. This is going to be a T dash thing. So let's say this is, if this is T which is developed as a tension in this string, so this will be T dash. Why? Because the strings taken here are different. If we take a little more complicated case, so let's say this is one body, this is another body, and let's say this is another body which is all attached to a fixed surface. So all these are attached to a fixed surface. Let's say this is of mass m1, this is of mass m2, this is of mass m3. Now there will be a tension which will be developing in this string. Obviously there will be a tension which will be developing for this mass m1. There will be a tension which will develop in this one. So let's say if we consider this as T1, let's say we consider this as T2, and we consider this as T3. So obviously this one will be T4. I hope we are clear on this one. So as many number of strings as we have, same number of tensions will we have. So whenever we change the string, the tension in it will change. So we have to remember two basic rules in order to solve problems with correlated to strings, wherein tension develops due to hanging of a weight. Tension doesn't necessarily develop just by hanging of a weight. It can also develop this way. So let's say this is basically a surface on which we are trying to move a body of mass m by applying a force F. So in this one, there will be a tension that will develop as T. So again, this will have a tension which will develop as T. So these are certain examples. Tension doesn't necessarily mean that it will always be suspended or hanging. It can be this way as well. So we will solve problems correlated to tension as well. But keep the concept very clear. For solving problems with regards to tension, we should have the tension going away from the direction of tension will always be away to the body to which we are correlating. So if we are correlating it to mass m, the tension T will act away. If we are correlating it to this surface, the fixed surface, the tension T will be acting away. Again, this one, tension T acting away from the surface, tension T acting away from the mass. Tension T acting away from the mass, tension T acting away from the surface. Again, tension T acting away from this mass, acting away from the surface. So this is how the tension T is always going to act. So this is the basic funda, and tension in different strings are going to be different. So these are the two basic criteria of tension. We will quickly look into the other contact force which we have, and that is basically the contact force of normal reaction. So very quickly, if we have a surface like this and there is a weight exerted by the body mg, so this body will have a normal reaction n. Just understand, these are although equal. If let's say this body is in equilibrium, this body is not falling down, neither it is moving up. So it is in vertical equilibrium. This is in vertical equilibrium. Again, equilibrium is connected to Newton's first law. How is it connected to Newton's first law? Just recall what is Newton's first law. I have written the second and third law there, but just try to understand what is Newton's first law. If the vector sum of all the forces acting on a body is 0, then the body is unaccelerated, which means that if we have a whole lot of forces acting on the body, whichever directions they are acting in, so let's say if we are adding it to this and this is equal to 0, then the net acceleration will be 0. So the body is not going to move, or if it is moving, it is going to move on with a velocity, a constant velocity. So net force, if net force is 0, then net acceleration produced in the body is also going to be 0. And that's what we mean by equilibrium. So let's say this body is in equilibrium, it is kept on a surface, it can be a ground, it can be a table, anything, and this has a body mass. There will be a normal reaction acting on the body. Now how does this normal reaction correlate? We will say that normal reaction n is equal to mg. But does that mean that they are acting against each other? No, they are not acting against each other. They are acting on different bodies. These are acting on different bodies. Different bodies. These forces are not cancelling each other. They do not cancel each other. They do not cancel each other. So we are referring to forces which will not cancel each other. So in this case, although the value of n is going to be mg, but they are not going to cancel each other. The n, that is normal reaction, is going to be exerted by, let's say this is body of mass, let's say this is body A and this is surface S. So normal reaction is exerted by surface S on body A, and the weight mg is exerted on surface S, exerted by surface S on A, and this is exerted on surface S by A. So this is basically by A, it is exerted on A. Exerted by surface S on A, exerted on surface S by A. So these are acting on different bodies. So normal reaction is basically acting on surface S, and normal reaction is acting on surface A and weight mg is acting on surface S. Hence they do not cancel each other. So we'll have to just remember these things. Let's say if we have something like this, an inclined plane which is inclined at an angle of theta. So we all know that let's say if this is basically the base and this is the perpendicular, and let's say this is the hypotenuse, and we have kept a body like this. So we all know that there is an mg which will always act vertically downwards. Why this mg is acting vertically downwards? Because the third type of contact force which we are going to deal with is gravitational force. And what we mean by gravitational force, irrespective of whether the body is in contact with earth or not, this will always be directed towards the center of the earth. So if we notice, this will always be perpendicular to the surface of the earth. This is basically the center of earth, this is the center of the body. This gravitational force will always be directed towards the center of the earth, and hence the acceleration due to gravity, which is a resultant of the gravitational force, this will also towards the center of the earth. This is the gravitational force directed towards the center of the earth, and hence the acceleration due to gravity will also be accelerated towards the center of the earth. So in this case we will always have the weight mg acting vertically downwards, that is perpendicular to the surface of the earth, and hence what we'll have is, so if we resolve this into components, we'll talk about resolving forces. So basically when we resolve a vector, let's say if this is a vector which is inclined at a certain angle theta with the horizontal, and this is basically the vertical. So let's say this is the y-axis and this is the x-axis. When we are resolving it, how do we resolve this? So very quickly, if I just look at the component of this force, this is the perpendicular direction, this is theta and this is the base. So whenever we are talking this one, base upon hypotenuse, so let's say if this is the base and this is the hypotenuse, what we mean here is cos theta is basically base upon hypotenuse, or we can say base is equal to h into cos theta. Base upon hypotenuse is equal to cos theta, or base is equal to h into cos theta. So basically what it means here is, if I have a force on this one, if I have to resolve this force, so if I have to resolve this vector A in this direction, it will be A cos theta. So this is my A, let's say this is B vector upon A vector is equal to cos theta. So we have here B vector will be equal to A cos theta. What it means here is I have resolved this A vector in the x component as Ax, and this Ax is nothing but A cos theta. So this is the vector, the one which is there with an angle theta becomes A cos theta, the one which is there at perpendicular becomes A sin theta. So in the same case we have here mg. Now look at this angle very closely. So we have this figure out here when we have this mg which is acting downwards, and we have this theta out here. Mg is acting downwards, obviously this will be 90, this will be 90 minus theta. So if we have to resolve this, I'll take some more space out here. I hope you have made a note of it. So this is a very important concept. Just try to understand how we are resolving this. So very quickly we'll resolve this. So just as we see if I have a vector like A and I'm resolving it into two components basically which are perpendicular to each other, this is let's say x and this is let's say y. So the Ax component, if this is the angle theta, is always going to be A cos theta, and the Ay component, which is this one, will always going to be A sin theta. And how is it coming this way? We have just shown it to you that if we drop a perpendicular here, if I drop a perpendicular here, so this becomes your Ax, and if I drop a perpendicular here, as we have an x and y axis, this is going to become your Ay. So Ax by Ax base upon hypotenuse will be equal to cos theta. So Ax component will be A cos theta, which means that this part is going to be A cos theta. And what we have here is Ay by A is equal to sin theta, which means Ay is equal to A sin theta. So this is going to be A sin theta. So that's how we are going to resolve this. So very quickly, if we refer to the same logic out here and resolve this here, we are going to talk about this in detail. However, I'm just trying to refer as to how the normal reaction n changes out here. So n will be always perpendicular to the surface. Normal reaction will always be perpendicular to the surface in contact. Surface in contact. What I mean here is, if this is the body and this is the surface in contact, so obviously the normal reaction is going to act perpendicular to this. Normal reaction is not, obviously it is correlated to mg, but mg will be vertically downwards. However, normal reaction will be perpendicular to the surface. So if we are resolving this, if let's say this body is in equilibrium, then if this body is not sliding down as of now, so how do we resolve this? Or even if it is sliding down, but the body is not moving this way, neither this way. So if I resolve this mg into two components, what do we have here? This is mg, this angle, let's closely look into this. This angle here is theta. So obviously this angle means 90 minus theta. So if this is mg, and let's say I draw a perpendicular component to this one, I am resolving mg into two components. Just as I resolved a into two components in the previous example, I am resolving mg into two components. Now this, the one that is attached with an angle of 90 minus theta obviously becomes the cos component, which becomes mg cos 90 minus theta. And we all know that cos 90 minus theta is sin theta. So we have here mg sin theta. So what do we have here? This will be mg, automatically this becomes cos theta. So one component will always be in sin theta and the other component will always be in cos theta. In this case, since it is mg, this component is going to be mg sin theta and this component is going to be mg cos theta. So if I look at it, since this body is not moving this way, neither it is moving this way, basically along the plane, so along the plane, the body is in equilibrium. Along the plane, body is in equilibrium, which basically means that the normal reaction and this force acting along the plane are equal, which basically means n is equal to mg cos theta. So this is how for inclined plane we derive the normal reaction. So n here will be equal to mg cos theta. So there are different ways in which we will be dealing with normal reactions, and we will be dealing with different examples as well, so that the clarity on normal reaction is pretty much there. Now for contact forces, I'll just grab a piece of chalk out here. Okay, now we will move on to the spring force and the friction as well. Just basic concepts about spring, we are going to deal with it in extensive manner. So whenever we are considering the case of a spring, whether it is attached like this, so let's say if I am moving this body in this direction, a force will develop on this string, and this force is basically nothing but minus kx. This is basically known as the spring constant. So for all types of springs, we will have a particular spring constant, and this x is nothing but extension in length. So what was the extension in length produced? That's going to be the force that will develop. So when I am pulling this body, there is a pull that is exerted this way as well. So the moment I leave this body after pulling, it will come back. Why? Because there is a restoring force. This is basically a restoring force. When I have disturbed a body from, so this is a restoring force which will, so in the string, because of its elasticity, there will be a restoring force which will pull the body back the moment this force is withdrawn. So when I am pulling a body with a constant force, there will be an extension produced in the spring. The moment I happen to release it, this will come back. Why? Because there is a restoring force that is applicable here, and this restoring force is basically proportional to the length by which I have extended the string. So this is pretty much about string. We are going to get into details about it. We also have cases like this, wherein when we have suspended a mass, this gets extended by a length x. Again, there will be a tension which will develop in the string, and this is going to pull it back. This tension will be equal to the restoring force that will be applicable on the string, and again this is going to act against the force. So if this is the force, the tension will act in this way. Again this will be minus kx. So this is how the spring thing works. and then we will have the case of friction. Again, as we know that friction is basically something which opposes the relative motion between two bodies. If we are moving a body with a force F, obviously the force of friction is going to act against it, and it will be after some time that this force of friction will start. We all know that friction is basically correlated to the interlocking of fine spaces that are there between the body. When we are looking at a body above the other, we generally do not realize that there is a lot of irregular surfaces between the two bodies. So let's say if I was to consider, I'm not extensively discussing friction out here, but since it's the contact force in which Newtonian mechanics is correlated to, I'm just giving you a heads up out here. So let's say if this is a body M of mass M and that is kept on a surface, so although we won't find any kind of interlocking, but between the finer spaces there is interlocking of spaces that has happened. So these bodies are basically both are irregular. Irregular means that they will have irregular patches all over them, and since they are irregular, these spaces will actually get interlocked between themselves, because of which you will have to apply a certain amount of force in order to make the body move. This body will not move unless the bodies are very smooth. Most of your problems you will find that these are very smooth surfaces. Smooth surfaces basically means that the force of friction applicable will be 0. Okay. So force of friction is applicable only when the surfaces are rough and there is a certain value of friction that is acting on it. So when I start moving a body, I actually overcome the friction, and when the body starts to move, then I will not have to apply that amount of force. The starting friction or the limiting friction will be more than the kinetic friction. So once the body is, so this is the basically static friction or the limiting friction, and this is the kinetic friction. Once the body is in motion, then I won't have to apply that much amount of force. Why? Because this interlocking of space that happened when the body is at rest will not happen when the body is in motion.